For this one, it asked me to do f of g of 2. This is my composition. So essentially what I'm doing is I'm doing substitution twice. I'm plugging the 2 into the g function, and then I'm plugging whatever that is into the f function. Okay? So I'm doing f of g of 2. So when I do g of 2, I'm plugging the 2 into the g function. That's going to be 2 squared minus 5, which is 4 minus 5, which is a negative 1. So now what I'm doing is f of negative 1, which means I want to take the negative 1 and plug it into the f function. And when I do that, it gives me a positive 1. And that's it. All right? Doing the same thing with the next one. I'm plugging it into the f function first this time. So I'm doing f of negative 4, which means I'm doing negative 4 plus 2, which is a negative 2. So what I have is g of negative 2. So I'm plugging the negative 2 into the g function, which is a 4 minus 5, which is a negative 1. And the next one is telling me to do f of 3. So I'm plugging the 3 into the f function, and then I'm plugging whatever that is into the f function again. So I'm doing f of 3, which is telling me to do 3 plus 2, which is 5. So now what I have is f of 5. So I'm going to plug that 5 into the f function, which gives me a 7. And that's it. It's just substitution multiple times. If I look at something like this guy, I'm given a set of ordered pairs, and I want to find f to the negative 1 of x, which is really my way of saying the inverse of f of x. Remember, the inverse, we just do the exact same thing, except we switch the ordered pairs. Instead of negative 4, 1, we do 1, negative 4. Instead of 0, 2, I do 2, 0. Instead of negative 1, 5, I do 5, negative 1. And that's it. That's my inverse. I do the same thing with my g function. I just switch each of the ordered pairs. So I start with the first one. Instead of 3, 3, I do 3, 3. I switch them. Instead of negative 1, 1, I do 1, negative 1. Instead of 6, 0, I do 0, 6. And that's it. That's my inverse. Okay, I switch the x and the y's.
All right, number 44, we want to use Pascal's triangle to simplify this binomial. And so we're going to use Pascal's triangle on the binomial expansion theorem. And Pascal's triangle, I've already got it written off to the side here. So now if I want to do to the 5th power, remember the top row is the 0 power, then 1st power, 2nd power, 3rd power, 4th power, 5th power is the last one I have written. So what I do is I write down these coefficients. So I write down the 1, the 5, the 10, the 10, the 5, and the 1. And then I fill in my a's and my b's. So over here I start with a to the 5th, and I count down a to the 4th, a to the 3rd, 2nd, 1st, and then a to the 0 means I don't write an a value at all. The b values are doing the same thing but going in reverse. So this is b to the 5th, 4, 3, 2, 1, and 0. And then I just slap plus signs in between here. So this is what I would have if I had a plus b raised to the 5th power. But instead of a plus b to the 5th power, I have x minus 2, which essentially just means that every place I have an a, I'm going to plug in this x. And every place I have a b, I'm going to plug in the negative 2. So I'm just substituting. Instead of a and b, I have x and negative 2. So I'm going to plug each of those in. So here I have x to the 5th. Here I've got x to the 4th times a negative 2. And I'm just substituting each of these. So I'm plugging in those values for each of these a's and b's. Oh, almost forgot to change that one. Let me try again. And now from here, I just simplify each of these terms. So I look at each term individually and I simplify it. Like this term right here really doesn't do much in the way of simplification, so it just stays as x to the 5th. This next term, when you look at it, I've got a 5x to the 4th times a negative 2. That's going to be a negative 10 x to the 4th. And so I'm just kind of multiplying these out. I'm doing exponents of multiplication. Here I have negative 2 squared, which is 4 times the 10 is a positive 40 x to the 3rd. And I just keep doing that. Negative 2 to the 3rd power is a negative 8, so that's going to be a negative 80 x to the 2nd. Here, negative 2 to the 4th power is 16 times 5 is a positive 80 x. And then negative 2 to the 5th power is a negative 32. Okay, so I just kind of multiply out each of these terms, simplify each of them, and now that's it. So this one's done. But again, that's much easier than writing x minus 2 out 5 times and multiplying it all out. In the next one, I want to rationalize the denominator. So for this one, what I need to do here in terms of rationalizing the denominator is I've got to go ahead and multiply this thing by the conjugate. Because what I want to do to rationalize the denominator, I want to get rid of all the radical terms from the denominator. And to do that with a binomial, I have to multiply by the conjugate, because that's going to cause the middle terms to cancel. So instead of 2 minus root 3, I do 2 plus root 3. Whatever I do to the denominator, I have to do to the numerator. Okay, and so I multiply these out. So in the numerator, I have to distribute or FOIL this thing. That's going to give me a 4 plus 2 root 3 plus 2 root 2 plus the square root of 6. In the denominator, when I multiply this out, again, it's FOIL or distribute here, because I have a binomial times a binomial. There is a shortcut we can take, but I'm going to multiply it all out. That's going to be a 4 plus 2 root 3 minus 2 root 3, and then minus the square root of 9. And now from here, I just have to simplify a little bit. Down here, the middle terms kind of cancel out when I combine those like terms. Up top, there's not really anything I can do, so I kind of leave it the way it is. If I could simplify, I would simplify square roots and combine like radical terms. Underneath, I'm going to have 4 minus. Well, down here, the square root of 9 is actually a 3. So what I have is this whole thing over 1, which means all I'm left with is this. And that's it. Okay?
For this one, it says find each value in graph. I want to find the vertex. To find the vertex, I do the opposite of b over 2a. So that's a 2 over 2 times 1, which is a 2 over 2, which is 1. That's the x value for my vertex. And then I plug it back in to get the y value for my vertex, which is going to give me a negative 1 minus 8, which is a negative 9. The axis of symmetry is x equals the x value from the vertex. The y-intercept, I plug a 0 in for x, and if I plug zeros in here, so it's going to leave me with this guy, the negative 8. For the x-intercepts, we have to plug a 0 in for y, so essentially what we're doing is x squared minus 2x minus 8 equals 0. And I can solve that by factoring. That's an x minus 4 and an x plus 2. So I find out that x equals 4 and x equals a negative 2. And really, that's just two separate order pairs. It's the 4, 0, and then a negative 2, 0. And for this one, since the a value is positive, the number that's out front is positive, means this parabola is going to open up, which means I'm going to have a minimum value. So now I just start to graph these things, and I'm going to scale this graph by 2's here. So 2, 4, 6, 8, negative 2, negative 4. Just because that negative 9 is not going to fit on here very nicely. So I do the 1, negative 9. It's right here. Oh, sorry, 1, negative 9. 1, negative 9 is right here. X equals 1. Axis of symmetry is this vertical dotted line. Y equals a negative 8. For my y-intercept, I can reflect that point over here. 4 and a negative 2 for my x-intercepts, and that's enough information to graph this thing. I get a nice looking parabola that looks like this, and that's it. Okay. Number 47, I want to graph this thing, and this is essentially in vertex form. There's my h and my k, so the vertex is 1, 3. So I plot 1, 3 is right here. I know that this is going to open down because the a value is negative, and it's going to be stretched vertically, so instead of going down 1 over 1, I go down 2 over 1. And I'm going to draw a V here because that's what the absolute value is always going to look like. It's just a nice V shape. And that's it. From this one, absolute value, again, the vertex this time is a negative 2, negative 4. Which is right here. And this one's going to open up because my a value is a positive 1 and have my standard width, which is up 1 over 1. So I draw a V that looks like this. And that's it. For this one, the The square root, remember, this is going to give me a sideways parabola, and depending on whether I have the positive version or the negative version, it gives me half a sideways parabola. But again, think of it this way as the vertex of being -3, 1. So -3, 1 is right here. I know it's going to open up because of the a value being positive. It's going to be stretched vertically. So instead of having my typical shape, it's going to be stretched just a bit. Look like this. It's half of the sideways parabola because I only have the positive version. And then this last one, the piecewise function. Basically, the piecewise function breaks the graph into these pieces. So x being less than a -3 is the piece that's over here to the left of this green dotted line. X being between -3 and +2 is stuff between the two dotted lines. And then x being greater than or equal to the 2 is the stuff to the right of the dotted line. And then I'm just going to graph a different function on each of these pieces. In this first piece over here, I'm going to graph this first function, y equals a -4. And y equals -4 is the equation of a horizontal line. It's this horizontal line right here. But what I do is I only graph it in the specified region. I only graph it in this first section. So I don't graph any of these pieces of it just in this first section. When I actually get to this line, I use an open dot because there's no equal to condition over here with my x is less than -3. Looking at the next section, this middle section right here, I'm going to graph this function, the 2x minus 1, which has a y-intercept of -1 and a slope of 2. And again, I'm only going to graph it in this section. So instead of graphing the whole thing and then having to erase pieces, I'm just going to graph the pieces in this section. On that first, over at -3, I'm going to use a closed dot because there's an equal to condition. Over here, I'm going to use an open dot because there's no equal to condition. And then the last piece of this thing, I'm going to graph the y equals a -x plus 2. So that has a y-intercept. And again, it's a y-intercept of 2 and a slope of -1, which would look like this. But I don't want to graph this whole thing. I only want to graph the piece that's over here. So I get rid of the pieces that aren't over here. I get rid of the stuff that's over on this side of that dotted line. So when I get a piecewise function, I use a closed dot here because there's an equal to condition. But a piecewise function, we get a graph that's in pieces. I have a little piece of one function, a little piece of another function, a little piece of another function. And that's it. I hope this was helpful, and good luck on your midterm.
Hello? Testing. Okay, I'm ready. Hey guys, it's Emily Hamburger speaking. Mr. Jansen knows math. Resume.